Hello, my name is Margarita Lopez Medina and I'm going to present my poster entitled Effect of Cobalt on the Martensitic Transformation Structure and Microstructure of Nickel-Manganese Gallium Alloys. In this work, a small amount of nickel has been replaced by cobalt in nickel 50 manganese 28 gallium 22 and nickel 50 manganese 30 gallium 20 alloys to achieve their martensitic transformation to room temperature, expecting to preserve the crystal structure of martensite in both alloys. The effect of cobalt addition on the martensitic transformation was observed by differential scanning calorimetry, the structure by X-ray diffraction, and the microstructure by optical microscopy. Nickel-manganese gallium alloys exhibit martensitic transformation between a high-temperature phase called austenite and a low-temperature phase called martensite. The austenite structure is a cubic L21 and the martensite, depending on the chemical composition, can be 5M or 7M modulated or non-modulated tetragonal. Recently, their elastocaloric effect associated with the martensitic transformation under externally applied stress has been investigated for possible application in solid-state cooling, but the reported values are relatively low due to their brightness. Therefore, ways to improve their mechanical properties are necessary. In particular, the addition of a fourth element can increase the toughness of the alloy and also make it possible to adjust the martensitic transformation temperature. Polycrystalline nickel-manganese gallium cobalt alloys were prepared by arc melting from high-purity metals in argon atmosphere, then were heat-treated at 1073 Kelvin for 24 hours. The differential scanning calorimetry curves were obtained using a TEA instrument model Q200 at cooling heating rate of 10 Kelvin per minute. X-ray diffraction analysis was performed at room temperature using a Rigaku SmartLab X-ray diffractometer. Micrographs were obtained using a Nikon Eclipse MA200 microscope. Figures 1A and 1C show calorimetry curves for the nickel 50 minor X, manganese 28, gallium 22, cobalt X, and nickel 50 minor X, manganese 30, gallium 20, cobalt X alloys, respectively. It can be seen that the temperature range of martensitic transformation shifts to lower temperature as the cobalt content increases in both series of alloys. Figures 1B and 1D show the evolution of characteristic transformation temperatures MS, MF, AS, AF, and the Curie temperature Tc as a function of cobalt content. In the case of nickel 50 minor X, manganese 28, gallium 22, cobalt X alloys, the transformation temperature decreases rapidly and the transformation range narrows with increasing cobalt content. Additionally, the Tc increases. In nickel 50 minor X, manganese 30, gallium 20, cobalt X alloys, the MS, MF, AS, and AF temperature decrease at a slower rate than in the prior alloys. Additionally, the transformation interval remains constant. Tc was not detected by this characterization technique in the ternary alloy and with 2% atomic of cobalt. However, Tc appears and tends to increase from 4% atomic. X-ray diffraction patterns of nickel 50 minor X, manganese 28, gallium 22, cobalt X, and nickel 50 minor X, manganese 30, gallium 20, cobalt X alloys at room temperature are presented in figures 2A and 2B respectively. The cobalt-free alloys correspond to 5M and 7N, respectively. The addition of cobalt in both series results in the displacement of the martensitic transformation at lower temperatures. Consequently, a mixture of martensite and austenite with low cobalt content and only austenite for cobalt 5 and cobalt A is observed in X-ray diffraction patterns, as can be seen here and here. These results are corroborated by optical microscopy images. In this alloy and that alloy, which have low cobalt content, typical microstructure of martensite is observed. Conversely, in the figures 2D and 2F, the typical austenite microstructure we can see. In conclusion, the addition of cobalt to nickel-manganese-gallium alloys results in the displacement of martensitic transformation to lower temperatures, towards room temperature, and TC to higher temperatures. This makes cobalt-doped nickel-manganese-gallium alloys an attractive option for caloric effect studies. The authors would like to acknowledge to CONACYT for the financial support, fellowship, and the Frontier Science projects.